This is our challenge problem from the last video, where Georgia begins walking from her house towards the east at 1 meter per second, and her brother begins riding his bike from the house towards the west at 6 meters per second. And we want to know after 1 minute how far have each of them traveled, and 1 minute is 60 seconds. So our distance for Georgia is going to be, oh, and I should clarify now, that distance is a scalar, so we're not concerned about directions. So that is going to equal speed times time. And for Georgia, that is going to be 1 meter per second times 60 seconds gives us a distance of 60 meters. Now our distance for her brother is going to be his speed times his time interval, which is 6 meters per second times 60 seconds, and that gives us 360 meters. Alright, part 2 asks who has the greater speed. Now remember that speed is a scalar quantity. So the direction does not matter. In other words, you could say who's traveling faster, and hopefully you'd realize from part A that her brother is going to travel farther, and he's going at 6 meters per second. George is only going at 1 meter per second. So the answer to this question is her brother. Part C asks a very similar question to part B, who has the greater velocity, where eastward is positive. So now we can take these values that I gave you in the problem and say that Georgia's traveling to the east. So she's going at a positive 1 meter per second. Her brother is going towards the west in the opposite direction at negative 6 meters per second. So this would give Georgia a greater velocity. And the final part to this question asks what would be the acceleration of Georgia's brother if he were to bring his bike to rest over the course of 10 seconds. So remember that acceleration equals the change in velocity over the given time interval. And this is velocity, so we're concerned about direction. So Georgia's brother's final velocity is going to be 0 meters per second, because remember this delta symbol means you take your final quantity and you subtract your initial quantity. So he's going to be at rest, so he'll have 0 meters per second minus his initial velocity is a negative 6 meters per second. In a time interval we have of 10 seconds. So this gives us 6 meters per second over 10 seconds. And that gives us a positive acceleration of 0.6 meters per second squared. Alright, now in this video we're going to be going over position, or you could say x, velocity, and acceleration graphs. These are a huge part about kinematics. And first let's go over the basic structure of the graph. So we have our y-axis and our x-axis. Now our x-axis is always going to be the independent variable, and that is time, which is frequently going to be measured in seconds. And then on the y-axis we have any one of these variables, which are measured in their standard quantities, meters, meters per second, or meters per second squared. Alright, let's start with position. So position graphs can look like, this is our time, it's not a good T, and this is our position. So they could be, for instance, a horizontal line. This would be an object whose position is not changing, this would be an object whose position is changing at a constant rate. This object would be speeding up, or this object would be slowing down. So the main thing that you can get from a position versus time graph comes from its slope. So remember that our slope is our change in y over our change in x. Now our y variable here is our meters, and our x variable is our seconds. And see these units? Remember that units of velocity are meters per second, and this means that the slope of a position versus time graph is our velocity. So looking back at our graphs, you can confirm what I've told you. This first graph right here has a slope of 0 meters per second, and it has no velocity, so it's not moving. This graph here has a constant slope, so it's moving at a constant velocity, whereas for these graphs you would take a tangent line, for example something that kind of runs to it like that, and you would do it at every single point on the graph, and you would see that here it's becoming steeper and here it's slowing down. So see if you can draw me a velocity versus time graph for each of these. Alright, I just realized I made a little mistake. This graph up here should be looking like this. At this point, if you were to draw the tangent lines, you would see that they are becoming progressively less steep as you continue along the time axis. So here we have a slope of 0, so our velocity graph would be constant at 0. For this position graph, we would have a constant horizontal line, but it would be positive above 0. And then here we have an object that is speeding up, so we would start from 0 and we would be getting progressively faster but at a constant rate. Whereas here we would be slowing down. So for this graph, if you were to start with your tangent lines, you would see that you start out positive and then you get progressively slower until over here you reach 0. So we actually start out with some velocity and it goes down to 0. Alright, now see if you can figure out what the slope of a velocity versus time graph is, and if you can figure out what the area of a velocity versus time graph is. So starting with slope, on our y-axis we have meters per second, and on the x-axis we have seconds. So if you multiply the numerator and the denominator by seconds, you would get meters per second squared. So that means our slope of a velocity versus time graph is the acceleration. And now area is going to be meters per second times seconds. If you were to do this triangle like that, you would have a 1/2, and that 1/2 is just a constant. I'm more so looking at this rectangle where the area is this part, height times width or length. Anyway, so you multiply your y times your x values and you would get meters per second times seconds, which just gives you meters, and that means that the area under a velocity versus time graph is your position. So going back to slope, let's see if we can draw the accelerations for each of these graphs. So why don't you go ahead and give that a try. Alright, so the slope for this first velocity versus time graph is obviously 0, and because we're at a constant position, you would expect that. So we just have 0 on our acceleration versus time graph. If you're on the AP exam and you're graphing something as 0, make sure you have a thick horizontal line down there so that your exam reader can see that you have graphed it and that you're saying it's 0. And the same goes for this graph right here, because we have a constant velocity, we have a slope of 0, so our acceleration is 0. Or this graph right here, we see we have a constant velocity, therefore we have a constant positive acceleration. And for this graph, we have a negative slope. So I'm going to extend this graph a little bit so that we can graph our acceleration as negative. These are all just rough sketches. We don't have any numerical values attached to them. So now I challenge you to see if you can figure out what the area of an acceleration versus time graph is. Alright, so the area for an acceleration versus time graph, which we have just a little quick sketch here, is going to be our y-axis times our x-axis. So on the y-axis we have meters per second squared times our x-axis we have seconds, and that gets us right back to our velocity versus time graph. And I just need to clarify a few things with area. So here's back to our velocity versus time graph. So the area for an acceleration versus time graph is the change in velocity, and the area for a velocity versus time graph is our change in position. So you don't really know unless you're told, for example, using this graph here, where the object has started. You know, it could have started over here, you just don't know. And the same goes for your acceleration versus time graph. It's your change in velocity, unless you're told its initial velocity or its initial position. Alright, to end this video, I have 3 challenge problems where I want you to sketch the corresponding velocity versus time graph and acceleration versus time graph. And then for this last one, I want you to find the change in velocity from this acceleration versus time graph. Units already given. The solution will be at the beginning of the next video, or you can find it on my Instagram page in the description 24 hours after the release of this video.